Hello and welcome to the Defense Tech Podcast. I'm your host, Civilian Sydney, and we are on episode 2 of our DoD-Critical series, where we're exploring the technology areas that are critical to U.S. defense systems with the 8 Hubs of Microelectronics Commons. Through conversation, the Hub leads are helping me and my audience understand the necessity of the technologies and infrastructure that they are building for future innovations. In this episode, I had the pleasure of speaking with Philip Wong and Tsu-Jae Liu from the Northwest AI Hardware Hub, based in the Northwest California region. Professor Wong holds his bachelor's degree from the University of Hong Kong, a master's in science from the State University of New York, and a PhD from Lehigh University. He has been on staff with Stanford University as a professor of electrical engineering since 2004. His works have contributed to advancements in nanoscale science and technology, semiconductor technology, solid-state devices, and electronic imaging. Professor Liu received her bachelor's, master's, and PhD degrees in electrical engineering from Stanford University. She has been a part of the faculty of the University of California at Berkeley since 1996, where she now holds the Roy W. Carlson Distinguished Professorship in Engineering. Professor Liu has had an impactful career in the industry. She holds over 10 awards for her work in electrical engineering and nanotechnology and semiconductor research. She has authored or co-authored over 500 publications and holds over 90 patents. I hope you enjoy this episode and stay tuned for more insights in the following weeks. All right. Hi, Philip and Tsu-Jae. Thank you so much for joining today's podcast. I'm really looking forward to learning more about yourselves and the Northwest AI Hub. So thank you and welcome on.
Thank you for the opportunity.
Yeah, of course. So I'd love if you could start by telling us a little bit about yourselves and your experience in the defense tech industry so far.
Okay, great. I'll start. I'm Philip Wong, professor of electrical engineering at Stanford University. I've been working on semiconductor for basically all my career. Started out at IBM Research and many years ago, and I joined Stanford 20 years ago. And but as you know, many of the advanced technology came from the needs from the Defense Department. And over the course of time, I've worked with various projects in the defense space, including projects from DARPA and IAPA and so on. And in particular, for DARPA, many years ago, I started working on the my advanced microelectronics program, which Tsu-Jae and others were in the same program as well. And Tsu-Jae would describe the accomplishments there. And also later on, we participated, and just recently, we participated in the DARPA 3D SoC, 3D system on a chip project, which basically translated the technology at Stanford on 2 technologies, one on carbon nanotube transistors, and the other one on resistive switching random access memory, RAM, to a US foundry, Skywater. And now Skywater has their products, have products on RAM, and also have a PDK, a process design kit, for the designers to use the technology. So those are some of the more recent work that we've done for the Defense Department and bringing laboratory scale technology to products in a US foundry.
Oh, great. Okay, what about you, Tsu-Jae?
All right. Well, hello, everyone. I'm Tsu-Jae Liu. I'm a professor of electrical engineering and computer sciences at the University of California, Berkeley. Like Philip, I've been working in the semiconductor industry for many years, and a lot of the research has been funded by DARPA. Philip mentioned the Advanced Microelectronics program. That was the program for which I and my colleagues at Berkeley developed the FinFET transistor. So this is the most advanced transistor used in high volume manufacturing of leading edge computing chips today. So when we developed the FinFET in the late 1990s, it took about a little over 10 years for the industry to commercialize that. So Intel was the very first to put FinFETs into high volume production. And today Intel is providing access to the government entities, the defense industry base, access to FinFET technology to manufacture the chips that they need. I've also had research funded by DARPA for even farther out applications, let's say in space, where we care about radiation hardness, but also ultra low energy consumption for electronics in space. So in that regard, I've been going back and looking at mechanical switches, which somewhat surprisingly, if you make mechanical switches just as small as transistors, they actually become even more efficient and energy and more reliable than transistors. So that's something that I'm excited about, looking towards the future to help our government maintain a technological lead, especially in defense applications.
Wonderful, fascinating. Thank you for sharing. So you two help lead the California Pacific Northwest AI Hub, which is one of the 8 hubs awarded under Microelectronics Commons in 2023. So could you both tell us about the hub? How was it formed? How do you guys get involved?
Yeah, so thank you for the question. Actually, Berkeley and Stanford have been instrumental in building the case for the establishment of the Microelectronics Commons, which together, Stanford and Berkeley leads the California Pacific Northwest AI Hardware Hub. It's a mouthful, because we have a very broad region that we are serving. We are serving Northern California, Pacific Ocean, and also Pacific Northwest. And our core partners are University of California, Berkeley, of course, UC Davis, University of Washington, Oregon State University, and University of Hawaii, and also a very important industry partner, Western Digital, which is a part of our core members. And of course, outside of in addition to the core members, we have the project teams, which comprises over 40 academic institutions, national laboratories, industry partners covering the entire value chain of semiconductors, from materials, devices, to electronic design and automation, EDA, and chip design, packaging, as well as system prototyping and testing, because the main goal of the Microelectronics Commons is to lab to fab translation. And so we are working very closely with many of the defense industrial base to demonstrate system level demonstration, not just devices or materials in isolation, but building complete system prototypes and testing. So that's the whole chain of materials, devices, design, packaging, as well as system prototyping are very important, and we have partners throughout the entire value chain.
Wow, it sounds like it ranges throughout the US and beyond, just because in my head, I know you guys cover AI, but it sounds like it's way more wide-ranging, more complex than that.
Yes, indeed. The Defense Department, when they call for topics for the Microelectronics Commons, they have 6 topical areas, and within each of the topical area, it would require collaboration across the entire value chain, from materials, devices, all the way to system packaging. And what the topical area that we have chosen, Tsu-Jae can expand on that, is the AI hardware innovation. And we are very focused in choosing only one topic to work on, because we believe this is our strength, and this is a unique contribution that we can contribute to the community. And Tsu-Jae, maybe you want to expand on the Hub's mission about AI hardware.
Yeah, I just wanted to enforce what Philip said. Our core partners, they were selected pretty carefully because they have unique facilities or proven facilities, or either physical or virtual, for that are open to many researchers in academia and in industry to prototype integrated systems. So the Hub's mission is really to facilitate translation of AI hardware innovations that have been developed by researchers anywhere in the country. We do that by providing physical as well as some virtual facilities for system level demonstrations, so that we can see the system level benefits of these hardware innovations, and also to check to make sure that they're commercially viable, that they're manufacturable, scalable. So our goal is to connect researchers from across different technical areas, so device technology specialists, designers, chip designers, and system architects, to build these prototype systems to facilitate faster translation of these innovations to industry, and to the benefit of our defense industry as well.
Yeah, wonderful. Thank you for explaining that. So, we touched on this that your tech area is Northwest AI. That's your main, or I'm sorry, it's AI hardware. That's your main focus area for your hub. So, what does your hub specifically bring to the table for this DoD critical tech area?
Yeah, so we are focused on AI hardware, and as you know, the AI hardware is basically developed in full strength in the Silicon Valley in Northern California. You see all the big companies that are working on AI hardware. They're all based in Northern California. Not only that, but also the other parts of the value chain, such as electronic design automation. Most of the EDA companies are headquarters and have the research centers in Silicon Valley. So, and also our key partners, of course, Stanford, Berkeley, and Davis and University of Washington, and so on. They have had very long experience in AI hardware. If you look at, for example, conference participation by these researchers, both in industry and also in academia, they are very active in the AI hardware space. And so we decided to focus on a single topic to have a bigger impact. And that is a very deliberate strategy that allowed us to dive deeper into the topic. And with that, we also have many industrial partners, especially foundry partners, such as Skywaters, MIT Lincoln Laboratories, Intel, and so on, and Western Digital, who are working alongside with us to focus on AI hardware. Of course, these companies have a very broad business scope, but we're also engaging with the specific segment of those companies to advance the AI hardware. And they're very excited about this opportunity because this is a chance for us to bring the academic research closer and faster into a product development stage.
Wonderful. Thank you for explaining. Do you have anything to add, Tsu-Jae?
Well, just to reinforce what Philip said, AI innovations, a lot of them, happened here in our region of the country, and I think it's so critically important for the future national security and this technological competitiveness. AI is so critical that's why we are focused on that, because we think it's actually the most strategic for our country.
Oh, yeah, great point. So, Microelectronics first recently awarded its first round of Call for Projects awards. So I would love to hear about the projects that the Northwest AI Hub was awarded recently in the first round, and a brief summary of each one, the intention of each project.
Yeah, great. We have been lucky to be fortunate to be awarded 3 projects, and I'll describe some of them, and Tsu-Jae can describe the rest of it. First project, what project I want to describe is the called Energy Efficient Scalable AI Hardware Systems through Heterogeneous Integration of Specialized Chiplets. Now, this is a mouthful, and each piece of the title means something very important. And first of all, energy efficiency is extremely important for any AI hardware because right now we are all constrained or gated by energy efficiency. For example, if you're flying a drone over oceans, then if there's not the compute engine is not energy efficient, that wouldn't last very long. So that's very important, energy efficiency, and it has to be scalable because it's a scalable hardware. So therefore, it cannot be just one chip. Has to be multiple chips together working in a system. So that has to be scalable to a larger scale system. Now, the method we use is through what we call heterogeneous integration of specialized chiplets. Chiplets are tiny chips that we could integrate together into a system. Now, each of the chiplets could do a different function, could be a special function. It could be fabricated using a different technology. Could be a logic technology, could be a memory technology, could be photonics. Could be integrate, and our goal is to integrate these things together in these different heterogeneous technologies into this chiplet. So the project really focused on designing systems using this chiplet approach and connecting different chiplets together. And this is a very strong collaboration between Stanford, Berkeley, and Raytheon Collins, as well as the foundry Skywater. So that's one of the projects that we're working on, and those chiplets aim to perform AI training at the edge. Now we all do AI training on big data center. You hear about companies building big data centers requiring nuclear power plants and so on. But that's a statement about the importance of energy efficiency, of course. But at the edge, namely devices at the edge, such as drones or anything that the combatants soldiers would carry, you also need high energy efficiency, but also you need training, because you may be seeing scenarios that the training data does not have already have. So you'll be seeing things in real time, and training in real time at the edge is important. So this project's focused on training at the edge. Right.
Okay.
The second one I would like to describe is led by Professor Ben Yu at. Oh, by the way, the first project is led by Professor Sebastian Mitra at Stanford, and also Barbara Lickowitz at the UC Berkeley, with our industrial partners, of course. The second one is led by Professor Ben Yu at UC Davis. They address energy efficient and scalable self-learning AI hardware with 3D electronic photonic integrated circuits. Now, this one, the keywords is electronic photonic integrated circuits. Why photonic? Because we have today the AI hardware chips the energy efficiency a lot of times is constrained by the need to shuttle the data back and forth between the memory units and the compute units. And the optical communication, photonic communications, would greatly reduce the energy required to shuttle the data back and forth. And so this project features very tight integration of electronics and photonics on the same chip. And so they will demonstrate commercially viable and multi-purpose optoelectronics AI computing prototypes that address really large-scale AI challenges in the chip scale. So Tsu-Jae,
thank you so much
you may
for
want to talk
explaining.
about the other project, which is very exciting for us.
Sure. All right. Thanks, Philip. So the third project that we were awarded is titled Integrated Ferroelectric Technologies for Ultra-Efficient AI Hardware, and it's being led by Professor Saif Salahuddin at UC Berkeley, and with many other collaborators. So over the years, if you look at Moore's Law, how it's advanced semiconductor technology, fitting more and more transistors on a chip, higher performance of the integrated system, the industry has integrated advanced materials along the way for the transistors and for the interconnections that determine the functionality of the chips. So the next wave of innovations, we believe, is really going to be due to integration of ferroelectric materials. Ferroelectrics actually already are used today to enhance the storage capabilities, charge storage capability of integrated circuits. So this project is aiming to substantially improve the energy efficiency of future AI hardware compared to today's state of the art. And the way that we will achieve this is by integrating ferroelectric materials, which allow the transistors to operate at much lower voltages than today's CMOS transistors.
Okay.
So we can lower the voltage, we can lower the power consumption, both static and dynamic power consumption. And I think most people realize today what's limiting the capability of AI systems is really the electricity usage. Like, we need to have like a power plant next to these huge computational centers in the future. And if we can alleviate that by, an order of magnitude, maybe, if not a factor of two, we can really help to expand the capability and adoption of AI technologies. So, I mean, the potential impact for commercial as well as defense systems would be enormous, because you just make AI more accessible. I mean, you can deploy it more broadly because you don't need as much energy to power the AI systems. And this, if you deploy AI more broadly, then you can improve the speed and accuracy and the intelligence of decisions, critical decisions that have to be made by defense systems.
Wonderful. Well, congratulations on all three of those projects. Those all sound very exciting, and thank you for explaining them. So I was wondering if you could dive a little deeper into the utilization of AI in this context, in the context of your three projects, because I know we all kind of have an idea of what AI is, specifically AI hardware. Can you kind of explain how that's different than how we might generally perceive what AI technology is?
Yeah, so basically the use of AI, I think there are two directions. One is um, microelectronics or semiconductors hope is the hardware foundation for executing all the AI applications. That's one direction. The other direction is the use of AI in helping further development of semiconductor technologies, and in both directions, right? And in this particular, in these three particular projects, we are mostly focused on the first part, building energy efficient hardware to improve to broaden the deployment of AI across the user space, and also enable some of the use cases that are not possible before due to the energy efficiency of AI. And the focus that we have is on the edge of the AI. There is so far, if you read the news, there's a lot of attention on building data center training models and things like that. But really, the deployment of AI for national security, for security needs, for the military, for DoD, is really at the edge. Namely, how would the soldiers in the field or the commanders in the command post use AI technology? And we're focusing on AI at the edge, training at the edge, not only influencing at the edge, but also training at the edge, because many of the use cases, as you go into the battlefield with unfamiliar situations, you cannot afford to have a model that does not cover that area. So you need to train on the fly. And this is something that we really need to focus on, and not only the influence at the edge, but also training on the fly. The other aspects that we are working on in these three projects is to exercise this flow of innovation, technology, and bringing it into production in the US. So in all our projects, we have foundry partners that are US-based foundry partners, and we have defense industrial-based companies working together to build this prototype demonstration. So by the time we get done, we will be able to translate our lab scale demonstration into a product line that these companies can offer to the DoD as they build their products. For example, we've been engaging with Skywater, a very common, very well-known defense contractors. Then Skywaters will be we will be bringing technologies into Skywater and making it available to broader use. Same with another engagement with Lincoln Labs, so the project that Professor Liu described, that we will be bringing those ferroelectric materials to work collaboratively with MIT Lincoln Labs, which will then in turn be able to respond to the needs of the Department of Defense.
Yeah, absolutely. That makes sense. So I would like to ask kind of a larger picture question. So how will these efforts in your projects kind of help with the larger microelectronics commons mission of re-onshoring microelectronics manufacturing capabilities in the United States?
Yeah, maybe I'll just describe one of the efforts that we're working on right now, which is part of the three projects. As you realize, all these three projects involve integrating unique functionality onto a base technology, the CMOS technology that we're all familiar with. So we call it CMOS plus X. So you can have photonics integrated with CMOS, you can have ferroelectrics integrated with CMOS, you can have other heterogeneous technologies such as resistive switching memory technology, such as oxide semiconductor gain cell memory technology, all integrated with CMOS. We call it CMOS plus X. And those have three different kinds of granularity. One is integrating, starting from a base level, integrating those materials into the processes itself, such as ferroelectrics, and integrating those devices onto the CMOS technologies, such as the gain cell memory, resisting memory, and so on. And also integrating these things into different CMOS technology plus X technology together into a system, such as the photonics and so on. So different kinds of integration on the CMOS space. And so our hub is these three projects all go towards our hub's overall vision of driving, enabling the CMOS plus X capability in the US, namely enabling the foundry to understand how the process of CMOS plus X would work, and using these three projects as an example to drive the development of these processes, so that eventually all the 8 hubs of the Microelectronics Commons will be able to use the same methodology to incorporate the new devices, new materials into a product technology. So that's kind of like a work in progress right now, starting with these 3 projects as sort of like a demonstration vehicle.
Wonderful. Thank you so much for explaining. Do you have anything you'd want to add, Tsu-Jae?
Well, just to summarize, I think the work of this hub can really help to bring up help support new foundries to have them have define a niche in the whole U.S. microelectronics manufacturing ecosystem, because as Philip alluded to, the trend is towards chiplet integration. So chiplets can be manufactured at different foundries which have specialized capabilities. So this will really help to diversify the supply of chips in the United States, and that's to the nation's long-term benefit.
Yeah, great. So kind of one more question for you guys. Do you think that, or why do you think that the Commons program has made such a big point of implementing workforce development initiatives into the programs? In your opinion, why is this such an important aspect of the program moving forward?
Tsu-Jae.
Okay, I'll take a stab at answering that excellent question. Especially in our hub, we actually have dedicated 20% of the budget for our hub for workforce development activities, because we do realize that there is a projected shortfall, that's this talent gap that is expected to grow in the semiconductor industry alone. And especially for the defense sector, we're concerned that even if we have the best innovations, if we don't have people out there at the cutting edge of using AI applications and staffing the foundries, and because they have to continually innovate and incorporate our innovations, the long-term economic prosperity, but also national security of our country is at risk. So workforce development is key to ensuring that the innovations we translate to industry will actually be produced in high volume in long term and used to the best advantage of the nation as possible. So, people like Philip and myself, you might tell, we're graying. So nearly 40% of the workers in the industry are over age 50, and less than 25% are under the age 35. This is from the Semiconductor Industry Association report from a few years ago.
Okay.
And it's surprising, a wide range of employees, talent is in our industry. So not a significant fraction of people working in the industry don't have bachelor's degrees. So there are jobs for anyone who's interested and motivated to work on our industry, and we want to empower them to be able to contribute and pursue rewarding careers in the industry. Now, California and Oregon, in Pacific Northwest alone, employ over 1/3 of the U.S. semiconductor workforce.
Really?
Wow. And Hawaii is also a major contributor in terms of the defense industry, talent, right? The military. So this is why I think, especially for our hub in our region of the country, since we're also home to many leading R&D centers, it's so important to support workforce development, attract the best and brightest students who will become, the engineers and technology innovators of the future. So we have leading chip manufacturers, equipment providers, chip design firms, lots of startups, so a lot of job opportunities in the Pacific Northwest region of the U.S. That drives the need for us to contribute as much as we can through our hub.
Yeah, absolutely. Well, great. So is there anything else that you guys would like to highlight about your hub or mention before we sign off today?
Yeah, sure. I just want to emphasize that Silicon Valley is the home of AI. GPU started in the Silicon Valley, and many hardware startups in Silicon Valley with great ideas to solve these domain-specific problems. And we have the best startup culture in the world with a complete ecosystem for innovators. A little while ago, somebody asked us to say, "Hey, does the Stanford and Berkeley have any services to support entrepreneurs?" Well, we don't need the support services because we have all the support services in the Silicon Valley itself. We have the entire ecosystem right here. We just need to walk across the street, and so we have the best ecosystems for innovators. And again, our hub, as Professor Liu mentioned, our hub allocates 20% of its operating budget to workforce development. We're focusing on 3 areas. One on regional technician training, because most technicians are regional, and so we focus on the regional training of the technicians, which we have a lot of R&D centers in the facilities in the Silicon Valley area, and those training, and also in the Pacific Northwest as well. So having technicians to support those research centers is absolutely important. And also we are very focused on chip design. Today we have a strong demand for chip designs. Students who have knowledge about chip design, because many companies want to design their own AI chips, and so our chip design courses are very heavily subscribed, and we want to develop open source materials for the chip design course, and also develop best practices and spread them out throughout, not only in our region, but also throughout the entire country. And of course, we have this K-12 engagement locally and so on. So this is the kind of things that we want to drive. We are very focused in AI, a topic that our region, California and Pacific Northwest, have a lot of strength on.
Well, thank you. Is there anything else you want to add, Tsu-Jae?
No, but if people would like to learn more and get connected or involved with us, I'd like to just point out that they can find a lot more information on our website. That's nw-ai-hub.org. And if you click on the page, visit the page about us, you can click on a link and subscribe, be added to our news mailing list.
Okay,
That's
wonderful. And if someone wanted to get to know about some of your workforce development initiatives, can they find them on your website too?
Absolutely.
Absolutely.
Awesome.
Please come to find it on the website, or just contact Professor Liu and myself directly.
Yep.
Okay, great. Well, thank you so much for coming on today. Really appreciate it. I definitely learned a lot. And I'm excited for you guys and your 3 projects moving forward.
Thanks
Thank
so
you
much.
for the opportunity.